part 2.
All right. So just sort of high level, where am I going? In the second part, I'd like to move on to sort of understanding a more general family of estimators. These are known as M-estimators in statistics, but they all have the same general form as the loci that we were analyzing. And what we're going to see is these ideas that we've picked up so far. Although they seem quite specialized, we were only looking at a least squares cost function. We were only looking at L1. We're going to see that there's a much larger family of estimators that these same basic ideas apply to. Okay, but before I did that, I just want to wrap up just a few things, just because I think there'll be some people that are interested from the first lecture. So I finished by deriving what's known as an oracle inequality. All right, so our oracle inequality says that if we have any vector, so theta star is any vector, it doesn't have to have sparsity assumptions. We solve this quadratic program with L1 regularization, then we get a bound of this form. Right, and it has two terms that often appear in statistical results. You have what's known as estimation error, this first term, and the second term is approximation error. Okay, so when you look at that, you can say, okay, that's a bound. And you can say, well, it seems sort of qualitatively reasonable. But I think a pretty natural question is it a good bound? Right? You could ask, are there much better bounds that could be proved? And certainly there are. For instance, these constants like 9/4 and 2, these are kind of artifacts. Those aren't sharp. But sort of qualitatively, we could ask, is there a much better bound that one could ever prove for this problem? And the way that you can answer that is you can answer it by, this is a very general result, but we can answer it by looking at more specific problem classes. So one kind of interesting set that people look at a lot, sort of the question here is, how do you relax a hard sparsity assumption? And one very natural way of doing it is you look at what are called LQ balls. I'm putting ball in quotation marks because these aren't really balls. These are not norms when Q is less than 1. These are non-convex sets that we're looking at. But the way it works is we have a parameter Q between 0 and 1. And we essentially take the sum of the absolute values to the qth power. Okay, so when Q is 1, then this is just the L1 norm. That is a convex set. It is a ball. And the L1 norm is in some sense a weak notion of sparsity. If you have low L1 norm, you're not exactly sparse, but somehow you're weakly sparse. Maybe more interesting is when you take Q between 0 and 1. If you take Q equals 0, by the way, if we sort of think anything raised to the 0 that's non-zero, that's 1. This is an L0 ball. It's something that actually encodes hard sparsity. But for Q between 0 and 1, you get these kinds of balls that look like this. They're non-convex sets. And roughly as Q goes to 0, you get a stronger and stronger notion of sparsity. Okay, so a corollary of that previous result is the following, that if you took samples, for instance, from a linear model, so y equals x theta star plus w, we assume that theta star belongs to one of these LQ balls. I don't need to know Q. It just belongs to one of them. The noise W has zero mean IID sub-Gaussian entries. That just means sub-Gaussian just means it has Gaussian type tails. So it's not too ill-behaved. Then what that oracle inequality implies is the following. It implies that the L2 error of any solution is at most the radius of your ball. That makes sense. As the ball gets bigger, you have more vectors that you might have to estimate. And then this makes sense. You have a noise variance. You should pay price if you have more noise. And then you have logarithm of the dimension over n. And you have an exponent, 1 minus q over 2. Right? That exponent ranges from 1. If q is 0, that's 1. And if q is 1, that's a half. Right? So your rate slows down. The exponent gets smaller as your sparsity model degrades. Okay, so let me just sketch how you prove this. This is a consequence of the oracle inequality. So under these assumptions, we're going to show the following, that the Lassus solution with high probability satisfies this bound. Just to be clear, when I write this little less than or equal to squiggly, that just means that I'm dropping constants that are are universal. They don't depend on the radius or the dimension or the sample size or Q. There are prefactors that I'm not tracking carefully here. Okay, so I think it's worthwhile. I'll probably truncate parts of lecture 2, but I think it's worthwhile just spending a little bit of time to illustrate because it's a fairly direct consequence of this. Okay, so remember in an oracle inequality we can choose this set however we like. Right? So we're going to choose it to trade off these two terms. And if you think about it, the only sets that are worth thinking about are sets of the following form. Sets that look like, for some threshold that I'll call tau, I'm going to look at sets of indices such that the jth coefficient in absolute value is big. It's a juicy coefficient that I'd like to estimate. Right? So this is a subset of possible choices, but it's the only one that makes sense because this thing for any other subset would be worse behaved. Okay, so the only question now is how do you choose tau? What's the right way to choose the thresholding operator? And so what you're going to do by choosing tau, you're going to keep a subset of coefficients, you're going to estimate them, and then you're going to drop the others and set them to 0, and you'll pay approximation error. Okay, so let's play a little game here. One thing we can say right away is that, so r of q is the radius, sorry, it's not raised to the qth power. There should be little q here, subscript. The first thing I want to do is I want to bound the cardinality of this subset. And my claim is that this is at least this large. Right? And why? Well, it's this large. Well, let's write it out longhand. Where's my eraser? If I don't watch out, I'll pull what Mike said that I tend to do, which is erase with my hand and then paint. Right? So we know that. This is a subset of these indices. There's cardinality s tau of them, and for each of them this is at least tau. This is q here. So this is at least tau to the q. Right? So rearranged, that implies the size of, as a function of tau, s tau is less than or equal to rq tau to the minus q. Right? This is valid for any tau larger than 0. Okay, so that's one term. That's an upper bound on this. Now I need to bound this term. So this term, what can I say? Right, so this guy is equal to the sum of things that are not in s of tau. By definition, theta star j to the qth, or not to the qth power, to the first power. I'm going to divide by tau and multiply by tau. Now, this object, by definition, this ratio is less than 1. Right? Because of my definition, if I'm not in this set, then I'm strictly less than tau. This is less than 1. Q is between 0 and 1. So if I raise this to the qth power, it only increases it. So this is at most j in s tau, theta star j tau to the qth power times tau. That's using the fact that q is in 0, 1. It wouldn't be valid for q larger than 1. And now I can take out a tau to the q, and I can upper bound this by r of q. So this is at most r of q tau 1 minus q. Right? So these are the two terms. That's important. And we've bounded the second term as a function of the subset. That's at most this. Okay, so now what you're going to do is you're going to plug these into here. You have two terms. It's going to be a function of rq of tau of lambda n. The way I'm going to choose lambda n is as proportional to root log d over n. That's a valid choice. And then I'm going to optimize. If you do the optimization, the optimal choice of tau is very simple. The optimal choice of, well, actually let me slow down a little bit just to clarify one important point. So how am I going to choose lambda n? Right, I need to worry about this random variable. What is this random variable? It's a maximum of j different random variables of this form, absolute value. Okay, so what I've assumed is that W has IID sigma sub-Gaussian entries. We're assuming that the columns of X are normalized. This means that you don't have one column that's sort of hugely larger than other columns. Columns are roughly of the same magnitude. It doesn't have to be unit norm. But under that condition, what you're looking at is roughly you're looking at fluctuations of variables that are, if it were actually Gaussian, these would be Gaussian variables that have variance of the order sigma squared over n, because you have a factor of n there. And you have p of them, so if you do a little d of them, if you do a union bound calculation, with very high probability this is going to be less than a constant times sigma times log d over n. Right, so that's that term there. It just means that I have to choose lambda a little bit larger than a constant times the noise variance times this ratio. So if you have that choice of lambda, you plug it in here. You have these two upper bounds, and you optimize. Right, you can see there's going to be an optimization because this is minus q. As tau goes down, this blows up. As tau goes down, this decreases. So it'll be a trade-off. Just do a little bit of algebra, you'll find that the optimal trade-off is very simple. The optimal tau is up to constants is root log d over n. Okay, so that's the right level at which you should threshold in your oracle inequality. And if you do that, actually there should be a sigma here as well, sorry. It makes a lot of sense because that's essentially the rate at which the noise is aggregating. You're sort of saying if I'm above the noise level, I'll keep you. If I'm below the noise level, I'll kill you. And if you do the algebra, then exactly the rate that I gave there falls out. Okay, so once you massage the different factors of tau into the lambda and do a little algebra, that's the exponent that comes out. Okay, so that's the use of an oracle inequality. Again, it's called oracle because I was kind of cheating as I chose the subsets. I mean, I'm cheating in the sense that the method's not cheating. The method is just the lasso. There's no cheating to it at all. But in the analysis, the oracle inequality is giving me the power to act in this oracular way and choose a good subset to trade off the two terms. So that's why we call these oracle inequalities. So any questions about that particular part of the argument? Yeah?
So I have maybe two questions. So gamma depends on S, I think, in your previous slide. And then the other question is...
Which gamma?
I think it's related, the gamma in the estimation and approximation error. That's the constant, the restricted...
So what this is saying, so gamma you think of as a constant. Okay. It's some number. You're correct that when I am assuming this RE condition, I'm assuming that it holds for this particular S. There's a slight technicality here that I've swept under the carpet, but I'm happy to talk with you offline about it. But think of gamma as constant. Typically, that's the way you'd apply this result.
So the other question is related to lambda n. So you chose lambda n as square root of log d over n.
Yes.
But if x columns are correlated, then maybe a union bound over there is loose.
Right, so that's a very good question. So his point was I chose it this way, and this is valid because just by union bound, this is the maximum of d sub-Gaussian things. His point is if x has very correlated columns, then a lot of these variables are correlated, so maybe the maximum's a lot lower. So there's actually some nice work by Johannes Lederer and one of his colleagues pointing exactly this out, that in general that is optimal in a worst case sense, but for certain x's you should be more careful in how you analyze it and actually choose it. So yes, you can get reductions below log d, but that's only for special kinds of x's. It helps a lot in prediction error, for instance. It's a good question. Anything else?
So Martin, I missed your first few minutes talk.
Yes?
So the Q norm 4 is a model for soft sparseness. Is that the...
Correct, yes.
Does it come from mathematical reason or from are there some sort of real problems, practical problems where This comes
There are many practical problems. So it mathematically comes out of the approximation theory literature. It's sort of a natural, this and what's called, this and what's called a weak L-cue ball, which is slightly different, are both natural models. But for instance, the work of Donahoe-Johnston, when they studied, all this work is quite old in some sense, at least in the case where X is just the identity, and you study wavelet thresholding, for instance. When you look at what are called Besov spaces, which are spaces of functions that are somewhat smooth but have bumps, so you can model interesting things like piecewise linear, piecewise smooth with jumps. What they show is that the wavelet coefficients, in a suitable sense, belong to slightly more complicated versions of these sets. So you can say if your model for some kind of signal class is that it's in a Besov space, then when we go to a wavelet basis, it translates into soft sparsity. So that motivated a lot of Donahoe-Johnston work in the 90s. Any other questions?
So I was going to ask why you're interested in that particular form, but I guess what you were saying is you might be interested in finding something close to that set of wavelet coefficients, which from more general considerations belongs in one of these spaces or around one of these spaces. And here you find it algorithmically with the lasso, some approximation at that level of quality. That's basically
right.
What the interesting thing about this.
Right. I think, so this is the general result, but it looks a bit scary, and you might say, well, what does it mean? This is somewhat more concrete. It's telling you in a particular model of weak sparsity, which we can discuss or suggest alternative ones, it gives a very concrete rate. And then the natural question you would answer is, okay, that rate is concrete, it seems reasonable, but you could say, is that a good result? Is that actually optimal? And apart from the leading constants, which are not being controlled well here at all, that is an optimal result. So let me just sort of close the loop by saying that. Right, so the point is you have an oracle inequality. That's a very general thing. You take a particular model, you look at it, it implies a particular result. Then we can ask, is that a good result or not? And we'll see, yes, it's a very good result. It's an optimal result. So again, Mike sort of suggested, Mike Jordan that is, that there might be some interest in lower bounds in this community. So I was just going to talk very briefly. One could possibly give a whole course on this, but he mentioned in his introductory lectures the notion of minimax risk. So let me just recap quickly. So I'm lifting up, talking for a minute about general statistical problems, then I'll specialize back to linear regression. Right, so the general view that one has in statistics is we have some family of probability distributions. We have what we call a parameter, which means it's some functional. If you give me a distribution, it spits back a number or a vector or a matrix or possibly a function, and that's something we'd like to estimate. So in my case, the parameter is just the regression vector. It's truly a parametric problem, although this could be, you could have functions as well. We have a metric on the parameter space. And so the natural thing that you could ask here is, suppose I give you n samples. Let's suppose, for simplicity, they're IID from some p. And I ask, if I look at the expected error using my metric, the expected squared error between your estimate and the parameter, and I look at this in a min-max sense. Okay, so what's going on? The max, I'm taking a soup over all distributions in some family. All right, so I'm allowing, this is in some ways a pessimistic view of nature. We're saying nature is adversarial, and nature is going to search a space of distributions and find bad ones for us. On the positive side, you as the computer scientist or statistician, you can take a minimum, an infimum over all possible estimators. Okay, an estimator just means you take n samples and it's some measurable function of n samples. Okay, so this is something called the minimax rate. It depends on the metric that you use, it depends on what parameter space you look at, and it depends on how many samples you have. Okay, so a very natural question here is, I've given you a class of models, right? These are models where y given x has a Gaussian distribution, let's say, with mean x theta star, variance sigma squared, and theta star varies over this ball. So I have a family of distributions. So I could ask, what is the minimax rate? Maybe I'll look at L2 because my bound here was, this is a particular metric. It's the distance between an estimate and the truth. So I could ask in L2, what is the minimax rate for that problem? right? So that's my family, that's my error metric. And so what tells us here is that that rate is good, is that essentially there's up to constant factors a lower bound that matches it. Okay, so when I write little squiggles like it means that there's a constant such that this quantity is upper bounded by that, and there's a smaller constant such that it's lower bounded by that. Okay, so that's one example of a minimax rate. And mathematical statisticians spend, at least a subset of them, spend a lot of time worrying about these kinds of functions. Actually, for computer scientists, there's sort of interesting variance on minimax rates. Right? Computationally, one thing that's slightly undesirable here is this infimum ranges over all measurable functions. Right? Maybe the infimum is attained by a horrible estimator that involves exponential time search. That is possible. What our upper bound here shows is that in this case, no, a very simple polynomial time estimator achieves the minimax rate. But that's not always the case. It's quite possible that maybe minimax rates are not polynomial time achievable. There's actually some interesting evidence in sparse PCA that that might be the case. Okay. Let me just, I'm not going to prove this, but I would like just to sketch very high level the machinery that's involved. I think it should be of interest to all the statisticians, but it could also be of interest to some of the theoretical computer scientists because they, of course, spend lots of time proving lower bounds. These are lower bounds of a different flavor because they're about statistical estimation problems, but I think the machinery is somehow more generally useful. So let me just sort of give you a high-level sketch. Actually, I know there's some information theorists here as well. A lot of the techniques end up becoming information-theoretic in nature, as you might expect. For instance, one method that's used is called Fano's method, essentially because part of it just uses an application of Fano's inequality. Okay, so let me just sort of sketch. I won't prove everything, but I think hopefully I can convey the... Okay, so this is an estimation problem. By estimation, I mean you're trying to estimate some parameter, a vector or a matrix, or it could be a function, but it's something taking values in a continuous space. The first step that people do is they reduce this to what's called a testing problem. Testing in statistics just means that you're trying to estimate something that takes a finite number of values. It could be binary testing, 2 classes, it could be emery testing. And the way that you do this is as follows. Sort of abstractly, let's think about as theta ranges over p, we get some parameter space, let's say capital theta of p. That's a set of possible parameters we might have to estimate. What we're going to do is we're going to form a what's called a packing set of this parameter space. So what I mean by a packing set, I'm going to form a 2 delta packing. So delta is a parameter that we're going to choose. By packing, remember I have a metric on my space. So I can take a collection of points, let's call them theta 1 up to theta m. And I want these points to be separated in my metric row by at least distance 2 delta. Right, so what you're doing essentially is you're taking a set of points, theta 1, theta 2. Around each point you're drawing a ball of radius delta, and you're asking that those balls don't intersect, right? Because I'm requiring this distance here should be greater than 2 delta, so that's saying that balls of radius delta don't intersect. Right, so it's a nice geometric object, and m is the cardinality of the packing. This thing has a name. It's usually called the metric entropy. It's the metric packing entropy when you take the logarithm of the number of balls. Okay, so this kind of thing goes back to, again, back to Kolmogorov. It's studied a lot. Okay, so the idea now is what I'm going to do is I'm going to choose one of these ball centers uniformly at random. you sort of think there's an isomorphism between ball centers and probability distributions. For instance, in my sparse model, if you give me a parameter vector, there's a linear model that I can draw samples from. So I'm going to draw n samples. I choose a model, I draw n samples, and I give those to you. And now the testing problem is I ask you to solve something slightly simpler. I say, just tell me which ball center I was drawing samples from. So it's a testing problem. It's an M-array testing problem over a packing set of M models. Okay. So where does the reduction come? Well, the reduction is in the sense that this problem is somewhat easier possibly than estimation. Right? So the intuition is if you had an estimator that was delta accurate, then with high probability, if I drew models from this ball, you would give me an estimate theta hat that was in this ball. And so I could just search over the cover for the nearest ball and I could solve the testing problem. Right? So the idea is, the reduction is that if you have a good estimator, an estimator that's delta accurate with high probability, then you also have a good test function that will have low test error. And that's formalized with a lemma. I won't prove, but it's a nice little exercise just to work through. Right? So what the lemma says is that if you look at the minimax risk here, this is lower bounded by delta squared in this case, times the probability over any one of my test functions. Right? So what do I mean here? So J here is an index that belongs to my index set, 1 through m. Those are indexing models. I draw that uniformly at random. And then, given that J is equal to some little j, then I draw these zi's from the model indexed by theta j. I equals 1 to n. Right, so that's what I'm doing. I'm picking a ball center. I give you n samples. And this thing here is a test function. It's a function that takes n samples and maps to an index. So what this is saying is for any test function, you can try and find the best one you want. Well, I should put an inf here. So I'm going to inf over test functions. Right, so whatever test function you do, then I have this lower bound here. Right, so that's the reduction, because what it says is I can lower bound the minimax rate by delta squared times, if I can make the testing problem hard enough that you fail at least half the time, then the minimax rate is lower bounded by delta squared over 2. Okay, so now what's the name of the game? Well, there's still work to be done, right? One is essentially a deterministic question, but there's a lot of work on this. You study the nature of different sets and you try and devise good packings. What you'd like actually to get a stronger lower bound is you'd like the packing to be as large as possible, right? I'd like to have as many hypotheses as possible to confuse you. If I'm adversarial, I want to confuse you as much as possible. So what you want is actually a maximal 2 delta packing, and for many classes the results about how big this is. And then the other part of the game is you have to lower bound the testing error. This is a testing error of an M-array problem from this simple model. Choose an index and then send samples. And so there's various lower bounds on this, both from information theory and statistics. One of them is Fano's inequality, which actually lower bounds this testing error by essentially you have log of the number of hypotheses and you have a mutual information. You get the ratio of those two quantities. That needs to be controlled. An older method people used is called Lecombe's method, and that in its simplest form actually just uses pairs of hypotheses, and then it lower bounds this by something involving the total variation norm. Okay, so there's a very large literature on this Ben alluded to. It's pretty classical, dates back to Hasminsky and others in the 70s. Berger in the 80s had some nice developments. Yang and Barron actually in fairly recently, or well, I'm getting old, 1999, Yang and Barron have a very nice paper in the Annals of Statistics that really makes a deep connection between these notions of metric entropy and it's sort of a very general use of the Fano technique. It's quite nice to read. Historically, actually, if you read Kolmogorov's 1950 paper, he has a 1950 paper in which he discusses metric entropies. In the appendix, this is roughly 6 years after Shannon, he's already connecting Shannon channel capacity and metric entropy in a fairly deep way. It's not fully there, but you can kind of, with retrospect, you can see that the seeds are there. So that's historically very interesting. Okay, so in this particular case, there's different ways to prove it, but the thing that you end up packing, in this case, you're packing an LQ ball. There's various results from approximation theory about such packings that one can exploit. And one way to prove this is using Fano's method. That's the way that was actually done in this paper. Okay, so any questions about that? Need a drink. Yes?
So the way you define the risk in terms of this metric, you are the metric you choose puts a geometry in a parameter space which you then use as heavily in all these inequalities. So to what extent are the results you can get robust to the choice of geometry you're putting on the parameter space? Because you can imagine some information-theoretic geometry on this thing. You're here using L2. People use L1 for a lot of these distances between parameters.
Oh, sure.
Does it change fundamentally? Is something one should worry about or not worry about? Or?
Well, the rates will change, right? Because if you pack a set using L1 balls versus L2 balls, the geometry is very different.
Right.
But at some level, they don't change they change in geometrically predictable ways. Okay. By the way, what I wrote here with squared is a special case. What people do is you can apply any monotonic function. It doesn't even have to be a metric. It can be a quasi-metric. So it's a very general theory. You can easily get L1 bounds, L infinity bounds. There's actually a paper by Zhang and someone else that does this not for L2, it does it for all the L infinity to L1 losses. The changes are kind of what you'd expect. It tweaks the exponent. You start getting different things other than 1 there. But you're exactly right. It's geometric considerations exactly because packings, the set stays the same, but the way in which you pack it differs. Anything else? Okay, so let me jump into alleged lecture 2. Okay, so sort of if we back up, what have I spoken about so far? We've spoken a lot about L1. We spoke about it in the noiseless case. We saw the importance of restricted null space. We saw some sufficient conditions for verifying it. And then we talked a bit about the noisy case, and we saw the idea of restricted eigenvalue. And we saw certain choices, perhaps slightly mysterious to you now, why the regularizer, this weight here, lambda n, why does that have to be chosen in certain ways? What I'd like to understand now, the time that remains, I'd like to talk a little bit about sort of more general perspectives, right? Because if we sort of look back in many different communities, we've seen an explosion of results about many different models, about L1, about block sparse models with group regularization, about nuclear norm regularization, matrix completion, graphical models. And all of these results, if we sort of take a somewhat more abstract view, they're all of the form that we assume there's some kind of low-dimensional structure. We posit some kind of cost function that depends on samples, and some kind of regularizer that enforces low-dimensional structure. And we're estimating by minimizing functions of this form. These are called M-estimators in statistics, M for minimization or maximization. So we'd like to understand do we sort of need to rederive results every time, like fresh, or is there some sort of common set of principles that we can distill? And I think there is a common set. I'm going to try and illustrate that. It's natural generalizations of certain decomposability properties of L1 and very natural generalizations of restricted eigenvalues. Those are the key ingredients. Okay, so first lecture I was talking all about linear regression. Many models are not linear. So as a slight increment of linear regression, we could look at regression where we have a more general conditional distribution, but such that the output you observe, yi, depends on an inner product between some unknown vector theta star and xi. Right? Why is this useful? Well, it would be useful. So a natural generalization of Lassou is you just look at L1 regularized likelihood. Again, you have a negative likelihood. It would be a convex function. In many cases, you'd have an L1 penalty. These kinds of things would be useful if I wanted to model binary responses. If I had voting data or other binary data, it wouldn't be appropriate to have a Gaussian, a linear plus Gaussian noise, but maybe a logistic model would be appropriate. A logistic model essentially models the response, the probability of seeing a 1 by a logistic function. And so you'd get a simple convex program, and you could wonder, can we say similar things about that? There's been lots of work on sort of structured extensions of sparsity. All right, so the L1 norm is basically saying that I think coefficients are on-off in an element-wise fashion. But there are many applications where coefficients naturally have some kind of grouping structure, and that we believe that when one coefficient in a group is on, then others are also likely to be on at the same time. One example, this is called multivariate regression. So here, instead of observing a single vector of responses, you observe a matrix, n samples of m possible outputs. So you're basically doing a vector regression problem. You have a matrix now that's m by d, that's unknown, and you might assume that the naive model would be the sparsity is just element-wise, but a block model would sort of say maybe rows are simultaneously on or off in an active manner. So if one coefficient is on, then the other coefficients in the same row are likely to go on. This comes up in things like gene array prediction, in graphical model fitting, in multi-view imaging. There are many cases where that simple model is motivated. So there's a natural generalization of L1 norm. In this simple case, you could just look at the L1 norm of the L2 norms of the rows. It's a convex function. It's again very much like a relaxation of the L0 norm applied to the L2 norm of the rows. Many generalizations. You don't have to use a 2 norm. You could use a general R norm. You can have weights. Your groups sometimes are not just rows of a matrix. More interesting cases, they're hierarchical or overlapping. Actually connecting back to, if you look at how wavelet coefficients are sparse, wavelet coefficients naturally live on a tree where the coarse coefficients live high up, and then as you filter down, you get finer coefficients. If you look at how sparsity manifests, it's not just randomly element-wise. You tend to see these, what computer vision people call scale space trails of large coefficients all the way down the tree. So what you'd like there is you'd like a regularizer that was somehow tree-based and enforced groups along the paths from root to leaves of a tree. And there's been a fair bit of very nice work on these kinds of more complicated group norms.
Just a question. Is it necessary to have all of these models being hit by the same X?
No, that's not necessary. I'm just drawing that as a special case. So yeah, the more general setting, I allow one x1 through xm that would be all different, and I'd have to reblock it and write it. But
wouldn't be different.
yeah, it's essentially the same. Well, it's a different model, but it's flavor-wise is similar.
Some restricted eigenvalue thing for all of those or something?
Yes, although I'll get into that. You'd have sort of a blockwise restricted eigenvalue condition. It's a good question. Anything else? So I'm going quickly just because this is sort of a high-level view. It's like a trip to the zoo where we see the exotic animals that are out there. This is an interesting problem. I mentioned in the first lecture, if you want to estimate inverse covariances that are structured, if you assume the inverse covariance is structured and it's Gaussian, you're basically putting conditional independence assumptions. And this is something that people call the graphical lasso. It's basically just the likelihood of a multivariate Gaussian plus L1 penalty on the off-diagonal edges. And so what you'd be asking here is I give you samples from a random vector that has a sparse inverse covariance, and then I ask, for instance, variable selection question is very interesting here. I ask, when does this estimate that I solve, when does this correctly detect the zeros? That is, when does it detect the missing edges in your graph? Right, so people use these models a lot, maybe sometimes non-Gaussian versions, but these are graphical models. You use these to model things like social networks or gene interactions, protein interactions, and so on. And there, the edges or absence of them, this is an interesting question. It's telling you whether these things are interacting or not. Okay, but the high-level story is that this is just another convex cost function, and again, we had L1 here. There's been a nice line of work on low-rank matrix approximation. Right, so here, what you're trying to estimate now is a matrix. Let's say it's D1 by D2. And what you believe is that it's, in the naive setting, you believe it's exactly low rank. All right, so if it's exactly low rank, then I could write its SVD with left singular vectors, right singular vectors, and a diagonal matrix of singular values. So R here would be the rank, would be much smaller. More generally, you believe that it's well approximated in some sense by a low rank matrix. And there's a very simple generalization of linear regression, is what's called matrix regression. Okay, so matrix regression just means that you observe the inner product between a design matrix now. Before we had the inner product between a vector and a vector. This is now just the trace inner product between a matrix and a vector plus noise. So it's a very simple model of matrix estimation. And this is a very natural estimator, again, least squares. What is this object? Did Ben talk at all about this? I don't think he did. About nuclear norm? I don't think so. So what is nuclear norm? Nuclear norm, these are just the singular values of the matrix. These are the things that are sitting on this diagonal. This is just the L1 norm of the singular values. So it has this fancy name. It's also sometimes called the trace norm. But the way to think about it is that a matrix has rank R if I took the L0 norm of the singular values, counted how many singular values are non-zero, the L0 norm exactly tells me the rank. But L0 norms are non-convex, and so by taking the sum, singular values are non-negative by definition, by taking the sum or the L1 norm, you're getting again the nearest convex relaxation. Again, this is a pretty old idea. Miriam Feisel in her thesis with Stephen Boyd studied this in some depth, but I suspect probably this idea had been around before. It's hard to tell, but so many literatures you might dig in. One special case of this that's been studied a lot, Ben, for instance, with Manuel Candes has done very nice work, is what's called collaborative filtering or matrix completion. That's the problem where your matrix, you sort of think of it as the rows might represent individuals and the columns represent films. The entries here represent things that have been rated. So people have watched these things and given them a rating 1 through 5. The stars represent things that you've not observed. So we can think about this, a naive model of this is that, how does it work here? These xi's, what are they in this case? These xi's are matrices that are 0 everywhere except for a 1 in some randomly chosen position. So if you do that and you take this inner product, then what you get is the matrix, one entry of the matrix plus noise. And if you do it randomly, you get some subsampling of the matrix entries. But the interesting regime is when many of the entries are not observed. You have many stars, so it's a missing data problem. For this collaborative filtering, probably this model is not really realistic. Probably more realistic would be something like a binomial model if you had 0-1 responses, or a multinomial model, but those are simple generalizations of this. Okay. Here's another cute problem. It's matrix decomposition. I mentioned this. People have studied a lot. It's an extension of both low rank and sparse. You imagine that you are interested in estimating a matrix that can be approximately decomposed into a nearly low rank and a nearly sparse matrix. And depending on the application, you might be interested in the sparse part, or you might be interested in the low rank part. One application of this is actually this problem here, where there was an interesting sort of intervention in the Amazon recommender system in early 2000, where what you had is people created spam accounts and put fake users in, and then these fake users took 2 books. They took 2 books. One was like a Christian spiritual revival book, and the other was a sex manual for gay sex, and they spammed both of them to have super high ratings, and they did this over and over and over again. So the effect was that the recommender system, if you liked this Christian guide, you would also like a gay sex manual. This won't work anymore. Don't try it. Amazon is obviously fixed. But essentially what you can think is, it's asking how robust are we to intervention. So the way to model it here would be, we'd have the matrix here would be a perturbation in which you have a fraction of the rows that are non-zero. You have a fraction of adversarial users. And what you'd like to do is, even in the presence of adversarial behavior, some fraction of adversaries, you'd still like to try and estimate the low-rank component that actually has meaningful information. So that's sort of a slight generalization with a row sparse instead of an element-wise sparse model. This was originally proposed by Chandrasekaran et al., a very nice paper. Bunch of applications. It's been followed up on by various people, and there's now a fairly good understanding of certain aspects of this model. Okay, so there's a bunch of other examples. I think just in the interest of time, I'll skip them. The slides will be posted, so you're welcome to look at them. Non-parametric models, I think actually there are many more open questions in high-dimensional non-parametrics than there are left in parametrics. But let me just get back to the high-level story. Okay, so the high-level story is that we'd like to sort of understand some general ingredients of analyzing methods of this type. And everything that I showed you in the previous slides, these estimation problems can be cast in this way. So what we're going to see is that there are really two ingredients. One is something that's called restricted strong convexity. It's really just a generalization of restricted eigenvalues to an arbitrary loss function. And the other is a certain geometric property of the regularizers that you use, and it's something known as decomposability. There are variants of it. Ben uses something called geometric decomposability. Sarah Vandegeer has something called weak decomposability, but I'll give you one flavor of this to give you the intuition. Okay, so let's sort of backtrack a little bit. In undergrad statistics, when you take courses, you learn about things like the log likelihood. You learn about the expectation of the second derivative of the log likelihood. That's the Fisher information matrix. And then you learn about the Cramer-Rao bound, which gives you a lower bound on how well you can estimate things as a function of the second derivative of the log likelihood. Right, so what's going on in all of these bounds? So why is the second derivative relevant? Well, the second derivative is just capturing some notion of curvature. Right, so we're trying to, the way I'm doing it, I'm minimizing the negative log loss. And the way to think about it, so maybe this is my log loss, my log likelihood. I minimize that, I get some theta hat. Now, what I'd like to do is understand how stable is that result, right? Because I only have n samples. If I perturb my likelihood a little bit, I want to see how much the solution would have changed. And the point is that when you perturb your likelihood a little bit here, you don't perturb your parameter that much. There's sort of a stability result that's a function of the curvature around the optimum. So when you have this kind of high curvature, it means essentially that if you perturb things in this domain, you get fairly small changes here, or actually conversely is what we're interested in. When we have low curvature, then the opposite effects. I can make small perturbations in the difference of the cost function, but I can make the parameters shift large distances.
If you're looking at the cost, changing the cost function because maybe your cost function is not perfect, but I don't know how robust the result is for that choice.
Right, so I'm looking at the cost function because that's all that I know. And you're exactly right, it's not perfect, because in a perfect world I'd have infinitely many samples. I have finitely many, so intuitively I should be concerned about fluctuations in the cost function. And if I'm trying to estimate parameters, I should be concerned about how those fluctuations translate into fluctuations in parameter space.
But fluctuations in like the empirical value of the cost function for the data, or fluctuations in whether you made the right choice of the cost function in the first place?
In this classical setting that I'm talking about, we're talking about log likelihood. So you could think either in the empirical version of the population, the curvature, one version is called the empirical Fisher information, the other is the population. In classical scaling, these are essentially the same thing. In high dimensions, we're going to see it's very different. Yeah, I mean a little loose here, but it's the correct intuition. It's spiritually correct, shall we say.
Like the Amazon.
Like the Amazon books.
I don't know if that was spiritually, that seems like spiritually incorrect. Okay, so how do we formalize this? This is very much connected to things that Ben was talking about, right? How do you formalize curvature in an objective function? In general, you look at the first order Taylor expansion, you expand it, now I'm expanding it around the unknown parameter in this case, and you require that it's lower bounded uniformly by some quadratic form, at least in the neighborhood of the truth. Okay, so high dimensions are interesting because that kind of picture can never hold. Right? So if we go back to least squares, if you have y minus x theta squared, Then if we look at the Taylor series area, the Taylor series area is exactly quadratic if you do a first order approximation. So you're looking at a quadratic form. And generically, when n, the sample size, is much smaller than d, the Hessian is going to look like this. There are going to be some directions that are very curved, but some in which it's totally flat. These are exactly the null space directions in linear regression that we spent the first lecture worrying about. Right? So it's clear in linear regression, but this picture is generically true. If I take any cost function, let's say that involves a sum of n terms, like in a log likelihood, this Hessian can be at most rank n when d is larger than n. So it's going to be rank degenerate. Okay, so the name of the game is, what we were doing before is we were sort of worrying about a very particular cone. And that cone, you can sort of think we were worried about, is that cone nicely aligned in these directions? We don't want the cone where the error vector can go in these bad directions. So essentially we need to somehow slide a cone, and that cone will come in one moment. But let me just formalize what we mean. Here's the generalization of restricted eigenvalues. So the generalization, because it holds for any differentiable loss function, and you can talk about it for any regularizer. Okay, so what you say is you look at the error in the Taylor series expansion. If your function is convex, this is always non-negative. But what you want here is that it's lower bounded by a quadratic form. If this term were not here, that's exactly strong convexity. But we have to put this term here. We can never expect strong convexity to hold. So I sort of penalize you, and I penalize you for directions in which you disobey the regularizer. So if you somehow don't obey the structure that I would like to see from the model, I'm going to penalize you. So there are two parameters here. There's a curvature parameter gamma, and there's a tolerance parameter tau. Okay, so let me just be concrete. So ordinary strong convexity is a special case. We've already seen a result of this form this morning. We proved a result, a random matrix result, which is showing that this kind of condition holds for L1. Right, so what did we prove this morning? We looked at least squares, and we showed that there's a class of matrices that with high probability satisfy this condition. So if you look at least squares, 1 over 2n y minus x theta squared. All right, so why is least squares so easy? Well, the Taylor error is just a quadratic form. The Taylor area is just 1 over 2n x delta 2 squared. Let's do a little calculation. And so what this condition would be saying, suppose I use the regularizer as the L1 norm as we were doing this morning. What we proved this morning is results of this form. We bounded exactly this quantity. Is there a 2 or not there? I think there's not. There's not a 2. Anyway, I'm very bad with constants. Right, so this is what we proved this morning, that there is a class of random matrices that satisfy this bound. Right, so what we're doing is just formalizing that notion for more general families. Right, so we're looking at restricted eigenvalues. That's because there's not a derivative here. That's because least squares has a simple Taylor expansion. There was a curvature constant, and the tolerance that I was proving it with was, again, something that depends on the dimension, but this was my tolerance squared. So that's an instance of one of these results for least squares. But we're going to think about this more generally. We're going to see that with many other regularizers, similar results hold. Right? There's nothing specific about least squares. We can do this for all sorts of other objectives. And there's nothing so specific about L1. We can do this for all kinds of other regularizers. Right? So the way to think about this is that if you have a convex function, then this difference is always non-negative. Right? So if you look in a direction where this term is larger than this term, then if this whole side is negative, then this bound is trivial. It's not saying anything interesting. So the way to think about this bound is it's enforcing a curvature bound, but only in certain directions. And these directions are very special. They're directions where the regularizer norm is small relative to, in this case, the L2 norm. Right? So if we think geometrically, when a function satisfies it, it means that these are all directions in which the ratio of the regularizer to the L2 norm is relatively small. Those are all curved directions, and all those directions are good. Okay, so any questions about that definition? Something that's sort of curious, actually, just a side comment, but this is a weakening of strong convexity, but it's not the same as convexity by any means. There are actually functions that are non-convex, but still satisfy that. And that's actually relevant for missing data problems. Often you have non-convexity in missing data problems. So it's not exactly the same as, it's not a subset of convex functions. It sort of intersects certain convex functions, but includes non-convex things as well. And geometrically, how can that happen? Well, just imagine instead of being flat here, I had a saddle function that started going down. Right? I can still be nicely curved in certain directions and have negative eigenvalues, let's say, in other directions. That's a non-convex function. It kind of is a monkey saddle, but it can still satisfy this definition. So it's sort of an interesting class of, it's an interesting condition, actually, just from an optimization point of view. It's related to some, there's related definitions of similar things in some optimization theory. Okay.
So what can you say in terms of optimization with respect to loss like this? Can you optimize them?
Yeah, so yes, you can optimize them, but yeah, so what you can do is you can optimize them quickly, as in geometrically fast, up to a small neighborhood around the optimum. And the reason you can do that is because as optimization problems, as long as I can ensure the algorithm always moves in these directions, it looks like a strongly convex problem. But what happens eventually is that as you get very close to the optimum, some of these directions start to intrude. So there's a certain radius of those directions. Once you're inside that small radius, you can't optimize quickly anymore. But actually, for many problems, you can prove that that radius is so small that it's below the statistical noise. So from a statistical point of view, you'd never want to optimize beyond that precision. But yes, Ben went through yesterday a sort of quick version of, he did gradient descent and contractivity. What this gives you is not global contractivity, but it gives you contractivity in certain directions. And that's enough to prove fast geometric convergence to a point. That's a great question. Yes.
I guess another question, maybe you're going to get to it, right? So I guess, what is the, so obviously this class of loss functions is more general than loss functions satisfy strong convexity, but what is the, I mean, I guess it goes back to Sebastian's question, is the intent here to try and define a larger class where you can optimize well in a way that sort of aligns yourself with the regularizer just by design? Because, I mean, what is the...
So the primary focus here, this has consequences for optimization, but the primary focus is to prove statistical error bounds. Right? So what we'd like to do, what our goal is you give me this, I'm going to assume that the minimizer of the population version of this, let's call that theta star, let's say it's unique. I want to give bounds on how far away this is from that population minimizer as a function of the structure. So I want to do this generally. That's exactly what we did for least squares in L1 and sparse vectors. I want to do this in some generality. So the point is that if you want to prove those bounds, you can never expect strong convexity, but this is a weakening that does hold for many models with high probability, and this is something that's useful. So that's the gist of it. Okay, so just right. So understand, if you understand RE, restricted eigenvalue, you understand this notion, because restricted eigenvalues just pop out in the special case of least squares. It's exactly the same intuition. It's a lower bound on curvature in certain directions. I think I'll skip this. Well, actually, no, let me state it quickly. But just to give you a sense, I've been talking all linear models, but let's talk on a somewhat more general family of models. Let's talk about what are called generalized linear models. Right? So these are models in which we have a conditional distribution of a response given covariates. that depends on the inner product between the covariates and some vector. That's unknown. It's a generalized regression vector. And then we have a kind of exponential family of this form. Okay, so why do statisticians like this? They like it because it includes many models we already know about. If you make this function t squared over 2, you get a linear Gaussian model. If you make this function log the logistic function, you get logistic model for binary response data. If you make it e to the t, you get Poisson data. So there's many models, many different kinds of data that we can model in this way. So here's sort of a general result on strong convexity. So we'll look at any regularizer that's a norm. It has to dominate the L2 norm. So it could be the L1. Dominates just means that it's in general larger than the L2 norm. So L1, group sparse norms, nuclear norms, all of these things are dominant in that sense. There's some interesting duality theory here. It's related to what Ben was speaking about this morning. It turns out that, so if you have a regularizer, you can look at its dual, the dual of a norm. So if I have L1, I get L infinity. If I have a nuclear norm is maximum singular value. Is sum of the singular values, and the dual norm is the maximum singular value, the operator norm. So any norm, we have a dual norm, I'll call R star. You look at what's called a kind of Rademacher complexity. It's a way of measuring how large is this ball. So you look at directions, you take a worst case over all directions in your unit ball, and you look at this random variable. These are your covariates, and these are random sign variables. That's something known as a Rademacher complexity. It comes up a lot in empirical processes. So here's a general result. There's actually no assumptions on the covariates other than their IID. What it says is that your empirical Taylor error will be bounded by the population quantity, and then minus a term that's of this form. And then t here, we have to plug into this equation. It says you need to choose t so that to make your probability small, it has to be somewhat larger than this random variable here. So that's sort of a uniform law. Holds for least squares, logistic, multinomial, all of these things. And essentially it reduces the problem of finding out, this is the tolerance term right here. To find the tolerance term, you just have to analyze this random variable. And that's a very geometric thing, right? What is that doing? That's sort of saying, let's look with these random signs in your covariates, let's look how far you can move out in a certain direction in your unit ball. Right? So for the L1 ball, this would be an L infinity norm. For a nuclear norm ball, that would be an operator norm ball. Okay. All right, so what that is showing is it's showing that in many cases, we can check that these kinds of conditions hold. So from now on, I'm sort of going to assume this condition holds, and I'm going to explore the consequences of it. And there's one more ingredient that we need, and that's this notion of decomposability. So let me move on to that. Okay, so up to now we've been talking purely about the cost function. We've been saying I want the cost function to satisfy this notion of being curved in some directions. If you think about it, the directions that are good here, right? Remember, the directions are good are directions in which the regularizer is small relative to the L2 norm. So what I need some way of translating between these two norms. And to do that, I need a geometric property that's known as decomposability. So what I'm doing here is I'm just formalizing the fact that when you take the L1 norm, it always splits into two parts. One part is if I take a subset, I can split it into L1 norm on the subset plus L1 norm on the subset complement. It decomposes exactly across those pairs of vectors. I just want to formalize this for more general losses. And so the way we do this is we sort of imagine there's some subspace. Think about it as a model subspace. It's where you think your model vector or matrix might lie. And there's a complementary subspace which is in some sense bad directions. Those are the things we want to exclude. And what we'd like, we're going to look at regularizers that are norms. You want norms, you want pairs of subspaces so that when you take something blue that's in the good space and something in the bad space, you want that essentially you can break the norm into two pieces and hit it separately on alpha and separately on beta. Right? So it's sort of saying for all pairs of vectors in these two subspaces, your norm decomposes. It breaks into terms on the two subspaces. All right, so it's obvious that L1 satisfies this, because if you take S sparse vectors and things that are supported off S, it breaks in exactly this way. What's more interesting is the nuclear norm on matrix space is also decomposable. That's not totally obvious to see. You have to construct the right subspaces. But what you can show is if you take a certain space of low-rank matrices and you define a certain complement in the right way, again, the nuclear norm will split. The singular values will split in the right way. So essentially, if you look at the analyses of all these kinds of norms, they're all using this decomposability property at some point. And there's some relaxations of this notion of weak decomposability of Sarah Vandergeer as one. Okay. So those are two ingredients. It's a certain property of a cost function, a certain geometric property of a regularizer. What can you say when this happens? Well, why is decomposability important? This is the generalization of the cone that we were looking at this morning. So what decomposability guarantees is that if you take lambda n large enough, remember lambda n is your regularization weight. If you take it large enough, then for any one of these regularizers, there's a very special set that your error vector has to belong to. Okay, so what are we doing? All right, so we're looking at this optimization problem. We've got this cost function, depends on the data. Well, this is some parameter space. It could be a matrix space. But a regularizer. We're assuming a restricted strong convexity condition on the Taylor series error. Right, so that's a property of the loss function. I want this to be bigger than some gamma times the 2 norms squared minus some tolerance squared of the regularizer. We have decomposability. And so now what we're addressing is how large should this quantity be? What's the minimal setting of that quantity? And this is essentially the correct way to set these in a variety of problems. Okay, so I have a regularizer that's a norm. So I have a dual norm, R star. Okay, so this is concrete examples. L1 would translate to L infinity for vectors. If I had a nuclear norm on matrix space as my regularizer, that would translate to an operator norm, maximum singular value for matrices. Right, those are two examples of dual norm pairs. So what the theory says is whatever norm you regularize with, first compute the dual norm. And then what you should do is you should look at the score function of your model. The score function is just a fancy name for the derivative of the cost function, evaluated at the true parameter. Okay, so when your model is well specified, that is going to be a zero mean random variable, because we're assuming that if I had infinite samples, then theta star minimizes it. So in expectation, the score function, that derivative, should be zero mean. And then what you're saying is you should measure the fluctuations of the score function in terms of the dual norm, and you should make lambda n a little bigger than those fluctuations. Okay, and if you do that, then good things happen. And what are the good things? There's always some cone. It's not always a polyhedral cone, but there's some abstract cone. And you're guaranteed that your solution and the truth, the difference between them lies in a very specific direction. Right, so that's why decomposability is important. Decomposability and this choice of lambda n, that's called the dual norm bound choice of lambda n for obvious reasons. It's sort of saying the way noise aggregates in these models is according to the dual of your regularizer. Right, and you can understand, just to connect to the theory I was giving you this morning and see why it's a special case. All right, so let's go back to least squares. I was talking only about least squares, and I was talking only about L1. All right, so we had least squares, and so our dual norm here is the L infinity norm. And what were my choices this morning? I was telling you that you should choose lambda n to be somewhat larger than 2 times x transpose w over n, infinity. Right? So that dual norm that's a special case of this. And for a linear model, if you compute the score function, for a linear model with least squares, this is exactly the score function. That's the noise. Right, so what we did for L1 is just a special case. The general story is look at dual norms and then choose the regularizer in this way. So any questions about that? I think if you want to understand the intuition, by the way, at least I personally like pictures, but this picture and this one earlier are essentially it, right? This is a picture of a generic high-dimensional loss function. It has bad directions and good directions. All you want to have happen, and what you do in these proofs, is you spend your time certifying that some cone-like set always aligns nicely in the good directions. Right? It's essentially a geometric thing. It's bad directions, good directions, and cones, and aligning them properly.
Yeah, so the function can be very non-convex because you have the regularization term which controls that. You also said that you use this to find an optimum up to a ball.
Yes.
And that optimum, if the function is not convex, it may not even have a minimum if it goes down like that. So it's not like, so you're finding the optimum not the original function, but the regularized thing up to that ball.
Okay, so to be clear, here I am assuming in addition that L is convex. There is more general theory that allows L to be non-convex as long as it's restrictedly strongly convex. The proof techniques are different, and you're correct, there are issues because if you have a non-convex function, you could escape off one of the slopes downwards. So there are some more technicalities, but roughly speaking, the results go through. Yeah, here, throughout, I'm assuming L is convex and R is decomposable. That's used to prove this a number of times. Yep?
What's M tilde?
Yes, where is M tilde? Yeah, so I've swept something under the rug a little bit here for pedagogical reasons. There are many norms that decompose across M and M twiddle, or M complement. But if you want to handle more general norms like nuclear norm, you have to introduce a third subspace that's a little bit bigger than M, and we call that M twiddle. So this is a general result that I think I deleted M twiddle from everywhere. But yeah, for nuclear norm, there's a slight augmentation of the definition, but the intuition is the same. Anything else? Okay, so here's some examples of verifying this. I'll leave them in the slides, but let me just state a theorem. Again, this is a deterministic theorem. From an optimizer point of view, it's a theorem really about stability of an optimization problem. Right? So what the theorem says is solve this program. It's going to be a convex program with a convex loss and a regularizer. We're assuming that you have this gamma tau RSC condition on your loss function with respect to the regularizer. Depends on the regularizer. And here's the first theorem. So the first theorem says, the first form of it says the following. It says that suppose you have a subspace M in which your true parameter belongs. Right? So in the case of sparse vectors that we did this morning, this would be a subspace of vectors that have a fixed support. It says, suppose this is less than 1. I'll come back to that. It says, be sure that you choose your lambda n big enough. Lambda n has to satisfy the dual norm bound. And then what it says is that any solution in squared L2 norm has error that's at most the regularizer squared, 1 over the curvature squared. So you have a curvature here. You have larger curvature, you get a better error. And a third quantity, which is a geometric quantity, which just measures when you look at your model subspace and you ask how much bigger can your regularizer be than your norm on that space. Okay? This is like a Lipschitz constant. It measures how large can the regularizer be compared to the L2 norm in a worst case sense over the subspace over which you're trying to estimate. Okay? So the intuition here is that as m gets bigger, this quantity gets bigger. If you try and estimate more complicated models, you're going to pay a price. The intuition here is that this is the score function. It assesses how much fluctuation, how much noise is there in your data. If your variance grows, this term is going to grow, so you're going to pay a price with the variance here. The third term is this curvature. If your loss function is more curved, it should be an easier problem, and so the error should be inversely proportional to that. Okay, so let me just rederive the Lasso very quickly as a corollary. Right, so for Lasso, what's your model subspace? You take M of S. It's a set of vectors in R of D that are equal to 0 when you're not on that subset. Right, that's a subspace. If I compute this psi squared of M quantity, it's the sup of vectors of the L1 norm over the L2 norm. Right? So these guys are S sparse. So what's the worst case? We did this calculation this morning. The worst case is root S. I already computed if I did least squares with L1, then R star of the score function for a least squares loss would have been X transpose W over N, infinity norm. All right, so as from the Lasso corollary, and we argued that in many cases this random variable is upper bounded by sigma times log D over N with high probability. So it means if you set lambda N a constant multiple of this, and I plug in the pieces, then immediately you get this bound. All right, so that's a special case. And the point here is not to have rederived the Lasso in a very complicated way. The point is that that applies to the Lasso, but it applies to many other things. And the rates that you will get out when you do other calculations look very, very different. But the point is, conceptually, there are really just three terms that are entering into all of these rates, and the three terms are very natural. One's a geometric curvature term, one is how the noise aggregates, and one is measuring how large your model is. Right? So that's the point. That's a deterministic result. And it has two essentially geometric assumptions, this curvature condition and a decomposability condition. Where probability enters is in verifying that you can find a pre-specified choice of lambda n that does satisfy that bound. And to do that, you need to assume things about your model, and you need to do some tail bounds and so on. But sort of high level, you can see there's a roadmap here of how you might derive bounds for many models. So any questions about that? Yeah?
You mentioned something about the square root lasso where you don't need the lambda and to depend on the parameters, right?
Yes.
Would you get it out of here?
No. So not immediately, because I was kind of assuming, I'm assuming things that are lower bounded by quadratics. Square root would not be. The reason why square root Lasso doesn't depend on it is because when you take the derivative of L2, you get just this. But if you take the derivative of square root of L2, you get this normalized by itself. You get a self-normalized quantity, and when you self-normalize, that normalizes out the variance. So this kind of analysis looking at score functions will tell you why square root Lasso has this nice property, but it wouldn't pop out of this. Yeah, it's a good question. Ooh. Any other questions? Yeah.
How difficult is it to get a handle on lambda when you switch to, say, logistic loss? Or just keep it at lasso, but with a logistic loss instead of L2?
It's not particularly hard.
Like what's involved, like instead of that?
Well, so if you look at any generalized linear model, what you'll get is you'll get a zero mean random variable, which is sort of a sample mean minus a population. If I was doing L1, I would again just have a maximum. For GLMs, let's say the cumulant function has an upper bounded second derivative. Those deviations are sub-Gaussian, so the same thing would hold. Poisson is hard, actually. I think you've worked on Poisson, or maybe Rebecca has. Poisson is hard because, it doesn't have its link function is kind of, or its cumulant function is a bit nasty. But for anything, logistic is very straightforward.
It's tricky, it's nice and bounded.
Yeah, logistic is fine. Yeah?
subspace term, so tolerance didn't enter your rate. It entered in some precondition. Why is that natural?
So the reason the tolerance enters is because when I compare this to this, exactly this squared is going to come out. And I need somehow that this gets dominated by that. So it comes out in using this condition to establish curvature in good directions. If I do the more general oracle version, let me just do that quickly. Right, so this is a general oracle result. So Shivaran was asking, why didn't your tolerance come out in the rate? It will come out in the rate here. Here you have to look at the worst case of lambda n and tau. And you'll get two terms. But a high level, so what's important here is this is the generalization. There's no assumptions on the vector. You take any subspace M, and you get a bound that involves how much you would have paid to estimate something if it lay in the subspace, and then you get a general approximation error term. Right? So we did L1. I just mentioned L1. So in L1, you project onto the orthogonal complement. Right? The orthogonal complement of this is just things that are 0 everywhere on S. So this is exactly the tail sum. This is actually theta star S complement. That's the approximation error you would have paid in L1. But if you do a matrix problem with nuclear norm, this will be a tail sum of your singular values. Again, a natural thing to have happen. Okay, any other questions? I think I'm nearing the end. I'm not going to finish everything I have. So there's a branching point. Think. There's some cute results which I'm going to skip. There's cute results about adaptivity to unknown structure that I will leave in the slides for you. Let me just talk quickly about low-rank matrices. Let me just rederive rates for low-rank matrices quickly. What you'll see is the rates look very different than sparse vectors, but high level, it's exactly the same things that are coming out. Okay, so let's just analyze this semi-definite program where we have a least squares cost. One instance of this could be matrix completion. That's a particular case of this setup. We have a nuclear norm, sum of the singular values. And let me just analyze the simple case where these xi's are random sub-Gaussian projections. But let me analyze it over a slightly interesting set just for fun. Let's analyze it over the set of the LQ ball of near low-rank matrices. This is a generalization of vector LQ balls where you look at the singular values and you ask that the singular values decay at a certain rate. Right? So for q equals 0, these are exactly low-rank matrices. For q between 0 and 1, these have a fast singular value decay. Okay, so here's a corollary of that result, that if you set the regularization parameter in a somewhat different way, why is this coming out? I'll show you the proof of it quickly in a second. So it has to be larger than this. You have curvature, then you will get this rate. And that rate is also minimax optimal. It's unimprovable. So let me just sketch why do these different terms come out. What I'll actually prove for you quickly, I'll just prove q equals 0. When q is 0, then R0 is exactly the rank. You're estimating over rank R matrices. R is the rank. Q is 0, this becomes 1. So let me sketch out that quickly. The more general result, again, requires trading off approximation and estimation. Okay, so what does our general prescription say? It says, in this case, we're looking at a nuclear norm. Right? We're regularizing a matrix with the nuclear norm. So it says first compute the dual norm. And I argued for you guys before that the dual norm is the operator norm, the maximum singular value. Right? Then what the theory says is it says compute the score function of your model evaluated at the truth. So if we do it for a least squares loss on a matrix problem, the score function is a matrix. It's a random matrix. And if you had a linear model, the score function would look like this, be xi. Right? These are your noise variables. That's what you've added. These are observed quantities. These are xi's. For instance, in matrix completion, these would be mask matrices, randomly 0 everywhere except for a position, a 1. And so what I need to do is I need to look at this random matrix and I need to derive a tail bound on this random matrix. Right? So there might be, depending on your model, there can be more or less work in doing that, but at least the recipe is clear. Right? So that's the probabilistic part of the calculation. Now, this is a very simple model. It's just a toy, but if these are actually random Gaussian matrices, let's condition on the noise, then this whole thing is a random Gaussian matrix with variance that depends on the L2 norm of the W's. But so condition on W, this is just a random Gaussian matrix. And I mentioned this morning that for random Gaussian matrices, there's lots of concentration and tail bounds. Essentially, you can show that in the Gaussian case, that random variable is upper bounded by 8 sigma times square root of the dimension over n, the 2 dimensions. So that's a high probability bound on the dual norm of the score function, and that ensures that my theory applies. Okay, so that's the dual norm bound. And then what's the last thing I need to do? Well, what's the right model space to look at here? Well, the right model space is, your model space is going to be a set of rank R matrices. In particular, you can look at the set of matrices that share the same left and right singular vectors as the true matrix. And if you look at the worst case of the nuclear norm over the Frobenius norm over rank R matrices, how large can that be? So if I have a space of rank R matrices, how much bigger can the sum of the singular values be than the L2 norm of the singular values? Right? You have essentially R numbers to play with. You only have rank R. This is equal to root R. Right? So now you can see where the terms come from. This comes from the choice of regularizer. That comes from measuring the size of the subspace, and the gamma comes from a curvature condition. All right, so that rate looks totally different than sparse vector estimation, but if we just think of it at high level, it's really just these 3 ingredients coming into play. Right? You're just seeing different instantiations of noise measurements and of subspace measurements. And to get the more general version, then you again have to play the usual oracle game.
So in that case, you're completely adaptive to Q.
Yes.
And is the RQ also the right dependence in the lower bounds, or is that a...
Over the relevant range, there's some corner cases it's not totally optimal. But let me just clarify the question. Right. So his point is that you're using nuclear norm regularization. You don't know Q. Your method does not know Q, but the method is what a statistician calls adaptive because it attains a bound that depends on Q and actually depends on Q in the optimal way. So yeah, when you do the lower bounds, it's again the same recipe. You have to compute metric entropies of LQ balls of matrices and so on. So there's some technicalities, but this is unimprovable. Yeah. So it is an interesting case that these are all cases where convex estimators seem to be achieving optimal rates, meaning that even if you could implement some non-convex or horrible exponential time search, you're not going to do substantially better. You might improve the constant, and there is a lot of work. People do worry about constants. I have not been. I've been very sloppy. But in terms of scaling laws, it is sort of interesting. These cases are optimal. Sort of an open question. There seem to be developing cases where convex methods are not currently known to be optimal. And one is sparse PCA, which essentially is a problem where you have a matrix that is sparse and low rank at the same time. They're very simple methods that achieve consistency, but they don't achieve minimax rates. They're not as good as what you would get out of an exponential time search. So that's, I think, sort of an interesting thing to keep your eye on. There are cases where convexity seems to be optimal and adaptively optimal, but there could be gaps, and I think understanding those gaps could be interesting. So that's basically all I had to say. I guess I'll wrap up there. Thanks.
Yeah, we're done for now. If there's any questions, any follow-ups everybody can ask? So back in here for one more talk. It is a boot cramp. You should be tired. That's a good sign. Back in here in 25 minutes.
Okay.